first in a series of screencasts in support of the MAR555 field trip, just looking at some model data from hindcasts of the Northeast Coastal Ocean Forecasting System developed by Professor Chen at UMass Dartmouth, essentially grabbing the data from the day we were on the cruise, September 30, and just examining it in the context of what we hope to get out of the cruise. So what you see before you is the larger domain model of NECOFS. The NECOFS data is available online. Just Google NECOFS. I'll just show you quickly the surface grid. So the model solves the hydrostatic primitive equations, and this is just the surface grid. You can see it's made of many triangles. If I cut out the bathymetry for a moment, you can see that how widely the mesh density varies. You know, something on the order of 50, 100 meters here, actually probably close to 200 meters here, tens of meters in this subdomain model here, and kilometers out on the coast here. And this scrunching of the mesh is intended to resolve the coastal features here. Excuse me one second while I enlarge my mouse. And coastal features here, as well as the shelf, the tidal mixing front and the shelf break front here. So this is places where the processes are varying rapidly in space, and so you use a higher resolution in those locations. And this was based mostly on a significant amount of trial and error and experience on Dr. Chen's part. This model went through many iterations over the course of 10 years. So this is today. So this is the large-scale region forecast from the Scotian Shelf down here to New Jersey. Actually, we're beyond Jersey down here. This is the edge of New Jersey. This is Sandy Hook here. I'm going to put the bathymetry back on here. I've truncated the range to 350. Otherwise, you wash out all the features in here because this is 1,500 meters off the shelf break. And what I'd like to look at is just to see, familiarize with the features. This is George's Bank right here. This is the Gulf of Maine here. There are three deep basins of the Gulf of Maine: George's Basin, about 360 meters, and Wilkinson and Jordan and Wilkinson Basin, which I can't recollect exactly how deep they are, on the order of 300 meters. And then we have George's Bank, this prominent shallow feature. So the Gulf of Maine looks like it's really quite open to the ocean, but because this is so shallow here, the deep waters of the Gulf of Maine are quite isolated from the deep waters on the other side of George's Bank. So there's two ways in for the sort of deep water. The key ones are the Northeast Channel. It has a 220 meter sill, and the Great South Channel that has a sill, I do not recall, 70 or 80 meters, something like that. Sill meaning that's the deepest depth if you cut across here. So water has to get across that to get into the deep water into the Gulf of Maine. And this is the shelf here. So our shelf extends offshore to about the 100 meter isobath, the Scotian Shelf, then this Gulf of Maine local feature, and then the New England Shelf going down to the Mid-Atlantic Bight. I think that's what I wanted to show you there. What I'm going to do now is put the wind field on for the day we were out in the cruise. Give me 1 second. And so this is the wind field. What you see there is the wind magnitude. Let me get rid of the grid, and I'm going to turn on the wind vectors. If I can find them, here they are. So it's not all the vectors. I'm only drawing some of them, and unfortunately, because they're placed on this irregular grid, they look funny and scrunched, and that's reflecting this local grid spacing. There's a way for me to make them uniform, but I'm simply too lazy to do that. But what you see here is what we were concerned about, or namely Miles, because he was making the decisions about the cruise, and there was a low pressure system offshore. It's actually outside the domain of this model, the center of this low pressure, and the low pressure in the northern hemisphere has associated at large scales with these cyclonic or in the northern hemisphere counterclockwise wind fields. A hurricane is another example of that. Was just a very much stronger low pressure. This was a fairly intense storm. You have winds nearing 20 meters per second, so that's 40 knots, so that's nothing to shy away from. And during the day, you can see that low pressure sort of comes into the model domain just sort of by coincidence. And it's moving basically south to north in our region. Oops, south to north. You see this prominent, I'm not sure what happened there, prominent cyclonic circulation. And the further you are from the center of this, the more the winds diminish. The wind vectors here are quite small compared to the wind vectors here. And so the path of these storms obviously reflects very strongly on how much wind we get here. We were concerned about Buzzards Bay, but as the week wore on, this storm track was further and further to the east, meaning we were getting weaker and weaker winds, and Miles decided that Monday made sense and it was fine. So, and associated with that, you see this, the wind magnitude in this band, and basically a circular band decaying down towards zero throughout the day, with distance from the center of the storm here. So that's the wind vector. I'll zoom into Buzzards Bay. We can have a look at the model data, and then if I have time, I'll grab the data from Buzzards Bay buoy, which is the local, the nearest high-quality source, I think, of wind data for our cruise. Although Woods Hole may have some as well. What I'd like to look at before doing that is just to go and see the significant wave height, model predicted significant wave height associated with this storm. And so that's what you're looking at here. And it looks very much like the wind magnitude that we just saw, just the scale has changed. It's 3.5 meters here, 3.5 meter significant wave height under the strongest winds of this storm. So they basically line up, they coincide. If I put on, and again, that follows sort of the wind pattern throughout the day. So the local wind forces generating these local waves. So ultimately these waves will wash across and land on Nauset Beach here. So here we call them local waves or wind sea, and here, you know, perhaps swell. It's, in this case, it's sort of the definition's a little loose. So the other thing I would like to look at here is actually, let's maybe look at the wave vectors. Those tend to be a little noisy, but we will have a look at them if I can. So what I've done is turn off the wind vectors and turn on the wave vectors. And let me just make them a bit bigger. I might have to return to this. I do not have them set up. I do not have that properly set up. Okay, that's better. Gotta pick a good scaling. Okay, so here's the wave vectors, and they're influenced by the wind generation. Some of them were generated, you know, previously. They're influenced by refraction across Georges Bank, because certainly these are big enough waves. They're starting to feel the bottom, at least on the shallow parts of Georges. So these are these wave directions. So they're essentially, at least the model prediction, impinging right on Cape Cod, which is right here on the outer part of Cape Cod. So this may have been a good day for surfing. There's fairly light winds there, with the sort of onshore waves coming in, and eventually reaching there. So the wave component of this forecast uses what's called a spectral model for waves. So if you've heard of Wave Watch, that's probably the most common one. That's sort of a global ocean spectral model. The Navy runs models as well, and they're all pretty similar. There's some discrepancies between them, but the spectral models, instead of, we're not resolving computationally every single wave. That is, I used to say that's impossible, although I saw recently was likely the most amazing simulation I've ever seen, which included 18 billion computational cells trying to resolve something like a 200, 300 meter patch of water, the entire wave spectrum from a realistic non-hydrostatic point of view. It was rather remarkable. But in general, for the whole ocean, this is beyond any computer power we could imagine for a very long time. And what's important is we want to understand, important things like significant wave height and period, because these are used for mariner forecasts. So the idea is that we can describe, the wave state, as we discussed in class, as a distribution of frequencies of how energy is distributed across frequencies and directions, and how that energy spectrum evolves with time. And that's what these models do, is they use empirical formula and physics from very smart wave people to understand how the spectrum is influenced by wind coming in. So wind is a source of energy, which tends to produce larger amplitudes or push the energy towards the lower frequencies. And wind, and then we have dissipation in terms of wave breaking, bottom friction, white capping. Those tend to take energy out of the wave and modify the spectrum, and then it's influenced by the presence of the bottom, etc. So the spectrum evolves around, and from the spectrum we can deduce important things like peak period, wave, significant wave height, etc., etc. So they're all similar. In this case, it runs in the unstructured grid. This is a wave model developed at UMass Dartmouth called S-Wave, and that's what you're seeing the results of here. I'll show quickly if I can, the period of the waves. Let's see if I have that for you. I may not have that. Give me 1 second. Okay, that is here, and we got TP. Switch that over, so it's about 2 to 12 seconds, something like that. And because the frequencies are discretized, they're discrete frequencies, or essentially describing our spectrum as a function of a set of discrete frequencies and directions, we see that in the period, that we have discrete peak periods in the model. Ranging from something like 10 seconds under the peak of the storm, and getting away from it down to 0. So there are places where the peak period and these things can be suspect, and those are generally, including direction, are places where you have almost no wave energy. So you've basically a very calm spectrum, and you're trying to derive these critical quantities from nothing, and you produce something, but that something is essentially meaningless. So the important thing is you have to temper this with a significant wave height. So if there are very, very small waves, then these other quantities essentially become meaningless. So let's zoom in. Hopefully my video is not running too long to be enormous. I'm going to try to do a zoom in on Buzzards Bay region. Only macro. 1 second. Let's go back to the wind field. Wind magnitude now, so it's going to be a lot weaker in Buzzards Bay, so let's go down to say 5 meters per second. That seems to be about right. And let me go back to my wind vectors, which do not have to be very large. Okay, and let's go back to the start of the day. I'm going to be a little bit too large. So I should have the boat in here. I'm not sure that I do. It looks like we need to change the range just a little bit. We are seeing close to 15 knots, so let me do 0 to 8. It's going to be a little closer, 0 to 7, I think. So again, the wind, when we were in the cruise, kept building throughout the cruise. This starts from 0 in the morning. My date is missing. Let me give you a date here. Okay, so 0 in the morning, 2 in the morning, 3 in the morning, 4 in the morning, 5 in the morning. This is low tide. Northeast winds all day, down bay, from the head of the bay to the bottom of the bay. So in an upcoming series of screencasts, I'm going to be talking a lot about how this wind forcing influences the bay. Even though it's not too strong, 15 knots, that's a low end of a typical sea breeze, you'll see it has a significant effect in the model predicted currents. And again, this wind field is also model predicted. It's from the Weather Research and Forecasting System. That's a state-of-the-art model that was the successor to the MM5. It's open source, and Chen's group runs a regional scale WRF model that's used to produce the wind stress, the heat flux for the ocean model, to drive the ocean model, and the wind stress needed to drive the wave model. All that's produced as part of this Neckhoff's package. So northwest winds is predicted. The low pressure again is off to the east. This is part of that quadrant. And just basically blowing down bay, about 15 knots here. So let me increase this to 8, maybe even 9. Let's see here. We can compare this with the wind from data from the tower. So towards the end of the day, in the afternoon, it was getting closer to 20 knots, or high teens. The wind was in the high teens, which is a significant source of wind. Now, let me just throw the significant wave height on here. At least during the cruise, it didn't have too much time to build because the winds were just picking up through the morning. And let's see if I can do that from here. I can. So I don't think it built much more than a ½ meter significant wave height. Most of the significant waves out down the bay. I put a line here which you can barely see, but there's a black line right here, and I can show the plot from that. Let me just change one thing. And this is working from the head of the bay, moving southwest towards the end of the bay, and you see that the waves don't really, wave energy doesn't really take off till the end of the bay. And as the day goes on, things start building. The wave energy is building up in the bay, and increasing. Now we're getting towards, actually we're in the afternoon now, but we're still seeing pretty small wave heights within the bay. And I actually think these are probably smaller than we saw realistically out in the water, and that could be from a number of factors. So, unfortunately, there are no good wave buoys locally that we could use to really examine the data. NOAA was going to put one right here, but they decided to put that in Nantucket Sound. I don't know why. So that's unfortunate. Buzzards Bay Buoy is somewhere down south here a bit. We will look at the winds from that. I think that's all I wanted to cover from this. So the next lecture or screencast will be talking more about Buzzards Bay setting, and then we'll focus only on Buzzards Bay from there. Here I just wanted to get a gist of the wind. The key thing, it's a northwest wind, is building throughout the, northeast wind building throughout the afternoon. It was a low pressure system far offshore, so this is a large scale wind field that we were experiencing. The summer winds are much more regional scale. It's a summer sea breeze. It's the opposite direction, pushes up the bay, typically June, July, August, and we'll see the influence that this either of these have on the structure of the bay currents are quite interesting. So a long bay, either up or down, produces some interesting flow characteristics. So let me just